You know that feeling, right? You're deep in your work, everything's flowing, and then bam, crash. It's got to be one of the most universal frustrations of modern life. But what if I told you that crash isn't a mistake? What if it's actually a clue? A clue to a mystery that goes back to the very beginning of computing. Seriously, why? Why do our apps, our games, the software we rely on every single day just stop? It's that moment of pure frustration. And a lot of the time, if you peek behind the curtain, you'll find a cryptic little error message that looks something like this. Ah, yes, the infamous stack overflow. Now, we're usually told this is just a simple memory problem. You know, the program tried to juggle too many things at once, and its short-term memory, the call stack, just overflowed. But what if that's not the whole story? What if this really common crash is a sign of something much, much deeper? Okay, so to get to the bottom of this mystery, we first have to really understand the official story. What exactly is a stack overflow? Why does everyone say it happens? Well, the textbook answer is something called unbounded recursion. Think of it like this. A function is a worker with a task. But to do its job, it has to give the exact same task to a new worker, who then gives it to another new worker, who gives it to another, on and on forever. Each new worker is like a block being added to a tower. And since nobody ever actually finishes the job, that tower just gets taller and taller and taller until crash. It topples over. Seems like a straightforward memory issue, right? Well, this is where our story really begins. Now, here's where it gets really interesting. According to the source material for this explainer, our everyday computer crash is actually the first clue in a decades-old mystery. And it connects it to two other legendary and what seem to be totally unrelated problems in the world of computer science. So, let's meet our three main suspects. First, coming from the world of pure mathematical theory, you've got Alan Turing's halting problem from way back in 1936. Then there's our familiar Stack Overflow, a system crash that really became a thing around the 1960s. And finally, from the shadowy world of cybersecurity, we have Ken Thompson's Trusting Trust hack, a total security nightmare he revealed in 1984. A paradox, a crash, and a hack. They come from completely different fields, different decades. I mean, what on earth could they have in common? So let's just quickly break them down. The halting problem is a theoretical limit. It basically proves that it's impossible to write a program that can look at any other program and tell you for sure if it will eventually stop or just run forever. Then there's the Stack Overflow. That's our system crash. A program gets stuck calling itself over and over and just runs out of road. And the Trusting Trust hack? Oh, it's a security nightmare. It's a way to teach a virus to infect the very tools you use to build software, which means it can secretly hide a backdoor in everything you create. Forever. A limit, a crash, and a backdoor. And to really get the chills from that security problem, just listen to this quote from the guy who invented it, Ken Thompson. The trusting trust problem means you can never be 100% certain your software is clean because the very tools you would use to check it might themselves be infected and lying to you. It's this dizzying, infinite rabbit hole of doubt. So we have a crash, a hack, and a paradox. They look different, they feel different, but the source material we're looking at today makes a bold claim. They are all just symptoms of the exact same hidden flaw, a flaw that was built into the very architecture of every single computer we use. And here it is. This is the hidden pattern that ties them all together, self-reference. In all three cases, the entire system breaks down the moment it's forced to operate on itself. A function calls itself, a compiler builds itself, a program tries to analyze itself. This one act, this self-reference, is the one thing our computers are fundamentally designed not to do. And this is such a critical distinction. The sources argue that this isn't a bug that we can just patch and fix, and it's not a physical limitation like the speed of light. No, it's a design flaw. And here's the kicker. It was intentional. The pioneers of computing made a deliberate choice. They traded away the ability for a system to handle self-reference, because in return, they got speed, they got predictability, and they got safety. They basically built a guardrail into the system, knowing full well it would create this blind spot. And that thinking leads us to this really powerful conclusion. A crash isn't the system failing. It's the system's safety mechanism doing exactly what it's supposed to do. It's the computer, honestly declaring its own limits. It was designed to prevent endless self-reference, and the crash is how it succeeds at doing that. So if our computers are actually designed to fail this way, what does that tell us about what they really are? Well, this design flaw reveals a really deep truth about the fundamental nature of our machines. The sources draw this fascinating line in the sand. Our computers today are mechanisms. They're like incredibly complex pocket watches. They follow a set of external rules to transform inputs into outputs. It's a straight, linear process, but they can't regulate themselves. Biological systems, on the other hand, are entities. They are self-sustaining, self-regulating. They operate in these closed circular loops, kind of like how a living cell works to maintain its own existence. Our computers were simply never designed to be entities. So what does all this mean for the future? Well, once you understand this fundamental design flaw, this hard line between a mechanism and an entity, it completely changes how you think about where computing is going, especially when it comes to AI. See, that boundary is everything. When you think about the holy grails of computer science, true self-aware AI, truly autonomous systems that set their own goals, software that can 100% guarantee its own trustworthiness, all of these things seem to require self-reference, self-regulation, self-awareness. They're all entity-level problems, but our current mechanism architecture by its very design can't go there. It might be fundamentally the wrong tool for the job. So, we're left with this final thought to chew on. The next time your computer crashes, maybe don't see it as a failure. Try seeing it as the machine being totally honest with you. It's telling you exactly what it is, a brilliant, powerful mechanism. And in doing so, it's also pointing toward everything it's not. And maybe, just maybe, what the next chapter of computing will have to become.